UPTC para dar inicio a nuestra charla 128 de nuestro evento Nuestro Encuentro. Damos un saludo especial a los colegas de la UPTC Duitama que se encuentran también en sintonía con nosotros siguiendo esta conferencia desde el canal de YouTube. Agradecemos al profesor Muhammad, quien nos va a compartir sus conocimientos sobre la temática de investigación que él trabaja, y dejamos al profesor Julián Serna, quien nos va a presentar a nuestro conferencista invitado.
Okay. Welcome everyone. Professor Muhammad Sajjad is professor of the Department of Mathematics in the University of Islamabad, Pakistan. Thank you, Muhammad. Welcome. Thank you for accepting our invitation. His talk is about data transmission codes over the Eisenstein Field. The screen is yours. Go ahead.
Start?
Go ahead.
Hello.
You can start.
Can I start?
Yes.
Okay. Good afternoon, everyone. At International Conference with theme Mathematicas UPTC Columbia. I am Muhammad Sajjad from Quaid-I-Azam University, Islamabad, Pakistan. Today I am here to deliver my talk focusing on the field of algebraic coding theory, and the title of my talk is Data Transmission Codes over the Eisenstein Field. I am very grateful to all the organizers of this international conference, especially Dr. Robinson, Jory and Sirna, as well as to the audience. First of all, abstract of my talk is, first of all, I will explain the basic concepts of algebraic coding theory. After that, I will explain a new field which is Eisenstein Field by using the ShortExec Sequence. After that, I will construct BCH code over the extension of the Eisenstein Field and the decoding of these codes. Information transmission system. If we have any message, this is the information source. First of all, we want to transmit this before the transmission. First of all, we will encode this message by using some adding redundant bit. After that, this is called encoding, and after that we will transmit this by a communication channel. So here will be the receiver, here is the encoder, and here is receiver. During this transmission, if any noise is occur, then first of all we will locate the location of the error. After that we will correct the error. So after this is called the decoding of any code. And if we want to get original message after removing the redundant bit, there are the following transmission goals. The length of the code must be small. Easy transmission of the encoded message. If the length of the code is small, then the transmission will be fast. So we cannot get a corrected code word. If the length of the code is very large, then the transmission will be slow and we can get the better error correction capability. So method of finding errors. First of all, if we have any message 0, because computer cannot understand every language, first of all, we will convert any message in computer language, and after that we can proceed this. If we have any message 0 and we want to transmit this, then we can get a 0 or 1. But we cannot, if we get a 0, then we get the original message. But if we can get 1, then this transmission channel is corrupted channel. So for this, first of all, we will add some redundant bit for the correction of the errors for getting the original message, we will add some redundant bit. The message length is 0, and after adding the some redundant 4 redundant bit, we will get a 0 0 0 0. But if we have a message 1, we will add some redundant bit. We add some 1 1 1 1, and this is called a encode. And also here this is a encoded message is 0 0 0 0. And if we have 1, we get an encoded message 1 1 1 1 and 1. I will explain some basic definition before the starting of the error correcting course. What is digit? Any number is called digit. But in CS language, computer language cannot understand every language. First of all, we will convert into binary language. This binary language consists on the 2 digits 0 and 1. What is the word? A sequence of the digit. Here are digits 0 1. A sequence of the digit is called word. Here we have 2 digits 0 1, and we can get a word 0 1 1 0 1 0 1, and we can get any other word by using these 2 digits. What is a code? A set of words. Here is a one word, but a set of words is called a code. So we can use these 2 digits. We get a word. More than one word is called code. Here we get 0 0 0 1 1 0 and 1 1. All of the code word has the same length. Here are 2 digits. Also same. Here are 2 digits. Here are also same 2 digits, and here are also same 2 digits. But in the second example, we get word 0 0 1 0 0 1. This is also a sequence of the digit, but length of each word is not same. So this is a code, but this is not a block code. What is block code? A block code having all its words having the same length. If the length of the word is same, then the code are called block code. In the first example, all the word have same length, so this code is called a block code. But in the second example, length of this word is 1, length of 0 1 is 2, length of 0 0 1 is 3. So the length of the word is not same. So this second example is not a block code. Code word. Every word from the C is called code word. Size of the code word. The number of element in a code is called the size of the code word. What is channel? Channel is any physical medium which information is transmitted. This channel may be radio, telephone channel, any other channel, mobile phone channel. You can understand any channel, communication channel, etc. What is noise? Noise is any, if we have a message we will transmit this by a communication channel. So this noise may be occur by the human negligence, by the sunspots, by the random disturbance, by poor writing, or by any poor hearing. For example, our language is Urdu language, but your language is a Spanish language, and I am speaking in English language. So if you cannot understand correctly, so this is called a noise. Noise of poor hearing or noise of poor languages. Redundant information. If we have a message against a noise, we can add some redundant bit. Then this is called a redundant. Extra bits. So this becomes a code. CN is become any code. be the receiver. Receiver, you can see that at this bit we get a different number. Similarly, at this bit we get a different number. Similarly, at this bit we get also. If this during transmission, if error is occur, first of all we will locate the location, this location, this location, this and this. After that, we will find the magnitude by using algorithms, algebraic algorithms or coding algorithms. So this method is known as the decoding algorithm. If we get an error, so we will remove the error from the receive vector, and after that we will get an encoding message, corrected code word. So at the final stages, we want to understand what is the message. So we will remove all of these redundant bits. We will get an original message this. Similarly, another example, we have a message with 0000000, and we will add some redundant bit 00000. So this becomes the code. From this digit to this digit, this was a message, but the whole becomes a code. And after that, we transmit this by a communication channel. Here is the receiver. He get a message. She get a receiver get a message in form of code. At this digit is 0, but the receiver get 1. At the last bit here is 0, but the receiver get 1. So it means that during transmission error is occur. If during transmission error is occur, then corrupted bits in the burst error. This is known as. This is another example. If we have information this, first of all, we add some redundant bit. This become a code. This is known as code word. Here was a receiver. He get a message after the transmission. So he get a message at a different bit at the second last, and similarly at this digit, he get a different number of digits in whole the receive vector. It means that noise is occur during transmission. So this channel is called noisy channel. So after that, can we get an original word? No, because this receive vector is not the original code word. So this is not the original word because this digit is different. So this we cannot get an original message before getting the location and error magnitude. If we get an error magnitude and location, then we can get an original message word. Binary symmetric channel. If we have a binary digit 0, 1, and if we get this channel, binary symmetric channel, help us to find the probability of error correction and also probability of error detection. So if we have a 0, if he get a 0 same, it means that for same entry, the probability is 1 minus p. For the different bit, for the different entries 0 to 1, because the probability of the event is 1, so the error cross probability is p, and the corrected probability will be whole probability is 1, so the corrected probability is 1 minus p. Similarly, for this one, the cross probability 0 is for the 0, the probability is p, and for the same probability is 1 minus p. So error correcting encoding theory, we cannot correct any error, and also we cannot detect any errors. Just we can correct the errors whose probability is less than half. If the probability of any transmitted code word is greater than equal to half, then we cannot correct the errors. Also, we cannot detect. It means that coding theory can correct or detect the error whose probability is less than half. For example, suppose we transmit the code word 111. So there are 4 possibilities. The receiver can get 111. Also receiver can get 110. Similarly, receiver can get 101. Receiver can get 011. But receiver cannot get 000 because the probability will be less than half. Similarly, receiver cannot get 000 because the probability here are 3 digits. So only one digit is changed. So the probability will be less than half according to this definition. So the correction probability according to this definition, if 1 is getting 1, so probability is 1 minus p. Similarly, for this 111, correction probability is 1 minus p for this one, 1 minus p for this one, 1 minus p for this one. So it will becomes 1 minus p into 1 minus p into 1 minus p. So it will becomes 1 minus p cube for this. Similarly, 110 for getting 1 minus p. Similarly, 1 minus p, and for 0 we get probability will be p. So it will becomes p into 1 minus p into 1 minus p. So it will becomes p into 1 minus p square. Similarly, for this 1 minus p, 1 minus p. So it will becomes p into 1 minus p square. Similarly, for this. So this error correction probability for any code word is this. So the error probability will be, because we know that the whole probability is 1. So the error probability will be 1 minus error correction probability. Now I am going to discuss the main work of my presentation. Many researchers are working in the coding theory on set of integers modulo n. Similarly, on the alphabet. Similarly, many researchers work on the coding theory by using finite field Galois field. But I am introduced another field whose name is Eisenstein Field. This is a vectorial algebra field, 2-dimensional field. We know that omega cube is the cube root of unity. So the sum of all cube root of unity is 0. Let z omega is equal to a plus b omega. A, b from the set of integer is the Euclidean domain. And the zp omega is a commutative ring with identity. So the zp omega is the Eisenstein field if p is equal to 3 or p is congruent to 2 under mod 3. Or zp omega is not field. But if we define a one class, this class is if p equal to 3, so it will become z3 omega. So it is a field. And also p is congruent to 2 under mod 3. Then these becomes a field. All zp omega are not field because all elements without 0 in zp omega are units if p equal to 3 or p is congruent to 2 under mod 3. This is the example Eisenstein field z2 omega. If p equal to 2, then this will become z2 omega. Element of z2 omega will be 0, 1, omega and omega square. This will be equal to 1 plus omega. This is the smallest Eisenstein field. And all element in z2 omega without 0 are unit element. And the cardinality of this field is 0, 1, 2, 3 and 4. The element in z2 omega are 4. So the cardinality will be 4. And the unit element in z2 omega are z2 omega minus 0. Without 0 all are unit element. So the cardinality of the z2 omega star, it means that the unit element in z2 omega are 3. These are the elements of the Eisenstein field z2 omega. Similarly, another example, Eisenstein field z3 omega. Because we defined If P equal to 3 and P is congruent to 2 under mod 3, these are all Eisenstein field. All others which are not satisfy this condition are not field. So Z3 omega consists on the 9 element and all are unit without 0. So the unit element in Z3 omega are 3 square minus 1. These are the element of the Eisenstein field Z3 omega. Here is 0, 1, 2 and all are others. It makes a symmetry. Similarly, another example, Eisenstein field Z5 omega. These are the element of the Eisenstein field Z5 omega. Because every element in this field are unit without 0. So the cardinality will be 5 square. And the unit element cardinality is 5 square minus 1. These are the element of the Eisenstein field Z5 omega. So in generally, cardinality of the Eisenstein field is P square. And the cardinality of the unit element in the Eisenstein field is P square minus 1. Now I will define a linear code by using Eisenstein field. So before defining the linear code, first of all, I am defining exact sequence. What is exact sequence? If we have a morphism phi 1, phi 2, phi 3 and phi n plus 1, these are many morphisms from one structure to another structure from same structure. So these structures A, B, C, D, X, Y, Z may be a vector space, may be a module, or may be a group. So if the image of phi n equal to kernel of phi n plus 1 for all n greater than equal to 1, so it means that this sequence is known as a exact sequence. And in this sequence, phi n is the injective map. It means that this is a 1-1 map. And similarly, phi n plus 1 is onto map. It means that this is a projection map. Now, what is ShortExec sequence? So this is a subpart of the exact sequence. In this sequence, we will get just two maps. One is phi A to B and second is phi B to C. So the first map phi is injective map, 1-1 map, and pi is onto map. So this is known as, if the image of first map equal to the kernel of second map, so it means that this sequence is called ShortExec sequence. Now I am defining a linear code by using ShortExec sequence over the Eisenstein field. First of all, I will apply the definition of the ShortExec sequence over the linear code nk. Here n is the length of code and k is the any message length. So ZP omega is the Eisenstein field. So we apply the ShortExec sequence. This definition. Here is the field ZP omega. Similarly, ZP omega and ZP omega quotient by image of phi. And the length of message length is k. Similarly, the length of code is n. So this is the injective map and this is the projection map. And this is isomorphic to ZP omega n minus k, because according to the first isomorphic theorem, ZPn and the element in the image of phi will be k. So this will be isomorphic to ZP omega n minus k. So if the image of first map equal to kernel of second, so this becomes a linear code. And this linear code C is the subspace of ZPn with length n, with message length k and the code length n. This is the example, linear code of length 2 and the message length is 1. Then how we can construct a linear code by using this? So here value of n is 2 and value of k is 1. The element of Z2 omega are 0, 1, omega and omega square. Omega square is, we know that omega square equal to -1 minus omega. But in Z to omega, we apply a mod 2, we will get 1 plus omega. And in the binary string form, these elements in written in binary string form. Now defining a linear code by using this. This is the Z to omega k. Here k is 1 and n is 2. So this will becomes n minus k, 2 minus 1. So these are elements of Z to omega. Z to omega consists on the 4 element because Z to omega is isomorphic to Z2 cross Z2. So Z2 cross Z2 consists on the 4 element. It means that Z to omega also consists on 4 element. And element of Z to omega are 0, 1, omega and omega square. Similarly, Z to omega square consists on the, this Z to omega consists on the 4 element and this is the 2. So it will becomes 4 square. It consists on the 4 square element with the length 2. So it means that 0, 0, 0, 1, 0, 2, 0 omega square up to so on. We get a 16 element by using Z to omega with the length 2. These are all linear combinations and also in string form. Similarly, Z to omega 1 consists on the 4 element. Now we will define an injective map phi. Phi means this is a 1, 1 linear map. So we will relate this 1 or 2 with 0 omega square. Identity map on a identity and all our other are linear because Z to omega consists on 0, 1, omega and omega square. So if we will multiply by this omega, we will get a different another map, another elements, this and this. So it means that this phi is 1, 1. Similarly, if all element of Z to omega square map on 0, it means that first image of phi equal to kernel of phi. So, and also satisfy the condition of the linearity, addition and scalar multiplication. So these becomes a linear code. These are the element of image of phi because these elements map on this, this, this and this. So these are the element of the C. So C is also a subspace of Z to omega square. It means that C is a linear 2-1 code over Z to omega square. Similarly, how we can generate a generator matrix by using this sequence over the Eisenstein field. So generator matrix G is a matrix whose order is k cross n. It consists on the all basis element of the C. In the previous example, C consists on the 4 element. So first is the linearly dependent. Similarly, all of 3 are linearly. So first, this is a linearly dependent, and also all of these are depend on each other because all of these are scalar multiple of each other. So it means that Z to omega consists on the Z to omega square has basis element omega square and omega square. So it means that the generator matrix consists on the all basis element of the C in row form. So G consists on omega square and omega square. These are the basis element of the C. This C. So omega square equal to 1 plus omega. Similarly, 1 plus omega. So we can write these elements in the binary string. This one and also this one. So this is a 1, 2 code. Here k is 1 and n is 2. So it means that it becomes a 2-1 linear code over the Argentine field Z to omega. Now I will explain a BCH code. Many researchers have worked a BCH code by using finite field. But in this lecture, in this presentation, I will construct these BCH code by using Eisenstein field. So this BCH code means Bose-Chaudhuri-Hickvingham code. All of these 3 are French mathematicians, Bose, Chaudhuri and Hickvingham. They worked on in 1959 and 1960 by using the element of finite field. So during transmission, these codes can be used in a data transmission, also in a telecommunication, digital storage system, secure information system and all our other transmission channels. And also this code can be used for the detection of the errors, robust errors, and all our other errors by using the different parameters. The main parameter of the BCH code is the minimum distance. If we increase the minimum distance, then the error correction capability will be increased. If we decrease the minimum distance D, then the error correction capability also will be decreased. So many researchers have used different algorithms. For example, Burlingame-Massey algorithm, also Euclidean algorithms, and many more. So in this presentation, I will construct a BCH code by using Eisenstein Field extension. We know that ZP omega is the Eisenstein field, and ZP omega is S is the Eisenstein field extension of degree S. It means that this is a quotient ring, ZP omega, and ZP omega X is a Euclidean domain. If we take a generator, this Fx, so this will be isomorphic to Galois field P power 2s. This is a quotient ring. And here Fx is the maximal ideal. This Fx is known as the irreducible polynomial of degree m over Zp omega. If we take a coset alpha, so it means that f of alpha equal to 0. So Zp omega alpha s consists on the set of all polynomials of degree less than s, and all these a0, a1, a2, as minus 1 be the element of the Eisenstein field. So this Zp omega s is known as the s degree extension of the Eisenstein field Zp omega. This is the example. Z2 omega is the Eisenstein field. Here P is 2, and the degree of polynomial is Fx is the ideal. This is the x square plus x plus 1. This is the primitive irreducible polynomial. Irreducible polynomial is an polynomial. If we put all elements of the field, then this is equal to non-zero. Here all elements of Z2 omega are 0, 1, omega, and omega square. If we put all the elements in this polynomial, we will get a non-zero. It means that this is a irreducible polynomial. And also a primitive means that alpha is the root. It means that it generates all elements of the space. Z2 omega square. It generates all elements. It means that this is a cyclic group of order P power s minus 1. So in this example, Z2 omega x quotient by 2 degree polynomial, it is a quotient ring, consists on the all polynomials of degree less than 2. And A0, for all A0, A1 element of the Z2 omega. So this is a irreducible polynomial, also a primitive. Alpha is the root. So it means that alpha square plus alpha plus omega equal to 0. So alpha square equal to minus alpha minus omega. It means that it produces all element of the multiplicative cyclic group of order 2 power 2 into 2 minus 1. So it becomes a 15. So these are element of the extension field Z2 omega 2 by using this polynomial. Here is alpha square equal to alpha plus omega, and alpha cube will be equal to alpha square plus alpha omega. We will apply a reduction map. We will put values of alpha square, and then after that we can get alpha cube. Similar process apply on all of others, and we will get a cyclic group of order P power 2 into s minus 1. So here it becomes a 15. For the construction of the BCH code, we need a minimal polynomial. If alpha is the element of the extension field, then alpha q square having the same minimal polynomial as px. Original polynomial is known as the minimal polynomial. In this example, if alpha is the element of the extension field, so first minimal polynomial will be x square plus x plus omega. So encoding of the BCH code over the Eisenstein field. These are the, first of all, we will let some parameters C, D, and Q. These are all positive integers. Here D is the design distance. C is any arbitrary constant. Q is a prime power, and N is the length of the BCH code. So it means that D will be greater than equal to 2, less than equal to N minus 1. Because if we take D equal to 1, so we cannot detect any error, because detection will be D minus 1. So 1 minus 1 becomes 0. So if D, we will take, so error correction will be T is equal to D minus 1 over 2. So also we cannot correct any error. So for this, Q is a prime power and N is relative prime to this Q. Let S be the least positive integer. Q power S is congruent to 1 under mod N. So this S is the degree of the primitive irreducible polynomial. So we will get all element of the primitive nth root of Z p omega S. It means that we will get all element of the extension field. We can see in the previous example. These are all element of the extension field. So we will use these elements for the construction of the BCH code. Assume, so this BCH code is consists on the generator polynomial, and this generator polynomial is the LCM of all minimal polynomials. MJX and variation of J equal to C, C plus 1, C plus 2, C plus D minus 2. Here C is any positive integer and D is the design distance. So all these minimal polynomials can be found be the element of ZP omega X. So we will use these conditions for J equal to C, C plus 1, C plus 2, C plus D minus 2. We will use these conditions and we can get all minimal polynomials. If this MJX divides X power N minus 1, it means that GX divides X power N minus 1. Because GX is the product of all these minimal polynomials. Similarly, if C equal to 1, then these codes are called a narrow sense BCH code. But if we take C equal to full length code Q power S minus 1, then these code getting by this generator polynomial are called the primitive codes. The number of the total code word in the Eisenstein field extension will be P power 2k. Similarly, this is an example. Construct a BCH code of length 15 with the design distance of 3 over the Eisenstein field Z to omega. So here the design distance D equal to 3, then the variation J will be equal to, and also C equal to 1, because we are constructing a narrow sense BCH code. So we will take C equal to 1. So this becomes 1, 2, and here D is 3. So 1 plus 3, 4 minus 2, 2. It means that we will stop at 2. So we will get a generator polynomial by using this J equal to 1 and 2. Here length of code is 15. So we will write this Q power M is congruent to 1 under mod N. Here N is 15 and Q is 2 power 2, 4. So it means S will be equal to also 2. So this becomes this Z to omega X quotient by X square plus X plus omega, because it consists on the 2 power 2 into 2 element, and unit element will be a 15. So we will use this table for the construction of the BCH code of length 15, because this is a cyclic group of length of order 15. So we want to find a generator polynomial, and this generator polynomial consists on the all minimal polynomials, MJX. So we need some minimal polynomials. First of all, if alpha is the element of extension field, then by using this theorem, if alpha is the element of the extension field, then alpha q square have the same minimal polynomial as px. So here q is 2 power 2. So here alpha is the polynomial, it becomes alpha power 2, it becomes alpha 4. Alpha power 2 into 2, it becomes alpha power 16. So in the previous example, alpha 15 equal to 1. So alpha 16 will be equal to alpha square dot alpha. So element will be repeated at this place. So we get just 2 roots for first minimal polynomial. So we will get these 2 roots alpha and alpha 4. And the third root will be equal to alpha 16. This will be equal to alpha. And we get the same element, we get a repetition. So here we get a 2 root alpha and alpha 4. So first minimal polynomial will be x minus this root and product of second x minus alpha 4. So after simplification and using these elements of the Eisenstein field, we will get this generator polynomial, this minimal polynomial. Similarly, for using the value of j equal to 2, it means that m2x generated by alpha power 2. So by using, once again, we will use this theorem and we can get 2 roots, these alpha square and alpha 8. And the next root will be equal to alpha 16, alpha 8 power 4. So we will get alpha square by using the element of alpha 15 equal to 1. So here we will get alpha square and alpha 8. So this is the second minimal polynomial m2x by using these 2 roots. After simplification, we get, for j equal to 1, we get a first root m1x. And for using j equal to 2, we get another root m2x. So gx is the LCM of all minimal polynomials. So these two minimal polynomials, first minimal polynomial is irreducible. We cannot factorize this. So the LCM of these 2 minimal polynomials will be the product of these 2 polynomials because first is irreducible. So after simplification, we get a generator polynomial gx. In a BCH code, we need a NKD linear codes. So here n of length of the code is 15 and d is given 3, but we need a value of k. We need a dimension of the code. So we can get a dimension of the code by using this generator polynomial because dimension of the code is equal to n minus degree of gx. Here n is 15 minus degree of gx is 4. So we will get 15 minus 4 equal to 11. So this is the dimension of the BCH code. So we can complete this BCH, narrow sense BCH code over the Eisenstein field 15, 11, 3. In the next example, if we increase the design distance instead of 3, we take 9. So error correction capability will be increased in the decoding process. So the variation of j will be equal to c plus d minus 2. So here d is 9, c is 1, it becomes 10 minus 2. So here will becomes 8. So if c equal to 1, so the variation of j will be equal to 1, 2, 3 to 8. So we need to find a generator polynomial like as the previous example. So first of all, we need to find out all minimal polynomials. If we take j equal to 1, then get a first minimal polynomial. Similarly, if we take j equal to 2, we get a second minimal polynomial alpha square. Similarly, if we use a j equal to 3, and so it becomes alpha cube, and we get a third minimal polynomial. Similarly, 4, 5, and 6 minimal polynomials. So this gx will be the product of all minimal polynomials because the first polynomial is irreducible. So the minimal polynomials, so the gx will be the product of all of these, and after simplification, we get a 11 degree polynomial. So the dimension of code will be n minus degree of gx. Here n is the 15, and degree of this generator polynomial is 11. So the dimension will be 15 minus 11 equal to 4. So the NKD narrow sense BCH code over the Argentine field z to omega is 1549 BCH code. In the previous example, if we take d equal to 3, we get a 15, 11, 3 code. But if we take d equal to 9, we get a 1549 BCH code. After transmission, if we have any receive vector, so we want to get a corrected code word. For this, we need a decoding. Decoding algorithm based on the Eisenstein field. We will use a Berle-Massey algorithm, advanced Berle-Massey algorithm for the decoding of the BCH code over the Eisenstein field. If C be any BCH code of length n with dimension k and the design distance d, then the code C is the null space of this matrix. If C equal to 1, then we can get a narrow sense BCH code. This is a decoding procedure. If we have any receiver messages R and C be any code word, so we have a NKD linear code which is narrow sense, then we can decode this receive vector by using the following step. First of all, we will find a syndrome, and syndrome consists on the product of receive vector and the parity check matrix transpose. This parity check matrix. And the length of order of R is k cross 1. 1 cross k, and order of H is n minus k cross n. So we will get a different syndrome. If all syndromes are 0, then it means that we get a corrected code word. There is no error during transmission. But if we get at least one non-zero syndrome, it means that error is occur during transmission. So if error is occur, then we need to find the location of error, and after that we need to find the magnitude of the error. So we will complete an error vector. After that we will correct this by removing the error vector from the receive vector. So we will apply a second step for the error location. So this is a modified Berle-Massey algorithm. These we will first of all we want to find this polynomial del ny. This polynomial can help to find the error correction and error magnitude. So these are the all initial conditions: 1, 0, 0, minus 1, and del n is the any polynomial which can help for the for finding the location of error and magnitude of error. And un is the degree of this del ny, and theta is the discrepancy. So first of all, we will choose first non-zero syndrome. If the first room is 0, then we will choose the second. But if the first two syndrome are zeros, then we will choose the third syndrome. But if all are zeros, then we cannot continue this process because there is no error. But if at least one syndrome is non-zero, then first of all we will choose here a first non-zero syndrome. After that, we will apply these conditions for the construction of del ny, and also and for the completion of this table we will use this. If in case 1, if theta n equal to 0, this theta n equal to at any place is 0, then this del n plus 1 will be equal to the next. Similarly, un will be equal to un plus 1. But in the second case, if theta n is not equal to 0, then we will find a del n plus 1 and similarly un plus 1 by using these conditions. First of all, we will choose value of m and n which satisfy this condition, and also n minus um has the largest value in the last column. So by choosing these values, we will find the value of the z, and after that we will put this value of z in this expression, and I'll also use the values of this. We can get a del n plus 1 for the completion of this column. Similarly, theta n can be theta n plus 1 can be found by using this expression. So after that we can get this, and this un is the degree of this del n plus 1. Similarly, n minus un can be found by using this column n and also this column un. At the completion of this table, we will get here a polynomial delta n. So first of all, we will find the reciprocal of this polynomial, and the all root of this polynomial. This reciprocal polynomial is known as the location of the error in the receive vector. Now we need to find the magnitude of the error by using this, and also using the elementary symmetric function. So it depends on the number of error locations. It depends only the number of roots. If the root are 2, then we will get here a 2-degree polynomial. If the root we get only one root, so here we get only 1-degree polynomial. If we get here value root get 3, 4, 5, then all of these depend on the degree of the polynomial. So we need to find the magnitude of the error. So we will use Forney procedure for finding the location, for finding the magnitude of the errors. If we get a magnitude of the errors, so it means that error vector can be completed by using the error magnitude and error location. So the corrected code word C will be equal to receive vector minus error vector. So this is a decoding, and this is an example of the decoding of BCH code. 15.11.3 BCH code over the Eisenstein field and the receive vector this. If we get a receive vector this, so we want to find the corrected code word if possible. So we will apply this algorithm, all of these steps. This example is very large, so I am explaining from the PDF. Here is a 15.11.3 BCH code over the Argentine field with receive vector this. First of all, we want to confirm that error is vector or not. So first of all, we apply a first step. We find a syndrome by using RH transpose. Here R is the receive vector and H is the parity check matrix by using the value of N and value of C by using this theorem. This is the H. Here N is 15, so it will be stop at 15 minus 1, 14. And C is 1. So we can get a syndrome by using the element of the Argentine field and the product of all these. So here we get a 2 syndrome alpha 7 and alpha 9. It means that all syndrome are non-zero, so error is occur. Now we will go for the next process for the by applying the Berle-Massey algorithm, this algorithm. So first of all, we will complete this table by using these conditions. So these are the iterations, and we get this table. So here we get finally we get a del n y. So we need to find the location of error by using this. First of all, we will find a reciprocal function of this. So the reciprocal function of del square y is 1 plus alpha square y. Now we will find the root of this. So alpha square is the root of this. It means that error is occurring in the receive vector at the second place, at the alpha square place. This is alpha naught space, this is alpha 1 space, and also this is alpha square space. So it means that error is occur at the alpha square place. At this place here is omega. So it means that error is occur at the place of omega. So after that, we will apply the elementary symmetric function and also Forney procedure. We get the error magnitude omega. So it means that error location is alpha square, error magnitude is omega. So E will be equal to 0, 0, omega, and all of others are zeros. So the corrected code word will be receive vector minus corrected minus error vector. So receive vector is 0, 0, omega, up to so on 0, 0 minus error vector is also same. So 0, 0 omega up to so on minus 0, 0 omega up to so on. So we will get a corrected code word 0, 0, 0, 0. So this is a trivial code word. If we want to confirm that this code word, this is a code word or not, so we will multiply this by a parity check matrix. We get a null matrix. So it means that this C is the corrected code word of the BCH code 15.11.3. Similarly, another example for the decoding of BCH code 15.11.3. Here is the receive vector is this. And also apply the same procedure. We get this polynomial, error magnitude is also same. So the corrected code word is this. Similarly, if d equal to 5, if we increase the design distance, then it means that error correction capability will be increased. So here d equal to 5, it means that here will be error 2 occurred, because t equal to d minus 1 over 2. 5 minus 1 over 2 equal to 2. It means that error correction, maximum error correction capability is 2. So by applying the parameters and algorithms, we will get a force syndrome, and all of these are non-zero. So after that, apply a Berley-Massey algorithms and all of these steps, we get a 2 locations. This is a table, and this is a reciprocal function, and also y1 equal to alpha and y2 equal to alpha 9. So it means that error is occur at the place of alpha power 1 in the receive vector and alpha 9 place in the receive vector. It means that error is occur in the receive vector at the place of this alpha and alpha 9. So we need to find a error magnitude by using elementary symmetric function and the Fourier procedure. We get a error magnitude z1 equal to alpha 4 and z2 equal to alpha 6. Sorry. So C will be equal to receive vector minus error vector. So this is called a corrected code word of the BCH code over the Eisenstein field z2 omega with design distance 5. Now I am explaining a local Eisenstein ring. This is extension of the Eisenstein field. This is a local Eisenstein ring, is a finite commutative local ring whose order is p power 2ns, because the degree of polynomial is s, and the p power 2n is the degree of the order of finite of Eisenstein field. And its characteristic is p power n. So the local Eisenstein rings p power 2ns equal to zpn x quotient by fx. This is a local ring. If n equal to 1, then it becomes a Eisenstein field. But if n is not equal to 1, n is greater than 1, so it becomes a local Eisenstein ring. So for the construction of the BCH code by using local Eisenstein rings, we need a basic irreducible polynomial. In Eisenstein field, we need a primitive irreducible polynomial. But in our local Eisenstein rings, we need a basic irreducible polynomial. For finding the basic irreducible polynomial, we will apply a Hansel's lemma. This Hansel lemma will give us a basic irreducible polynomial by using primitive irreducible polynomial. This fx bar is the primitive irreducible polynomial from the extension of the Eisenstein field. And this order of this is equal to this. And any irreducible polynomial is called a basic irreducible polynomial. If we apply a reduction map, then we get a polynomial which is the primitive irreducible. So this lemma can provide a basic irreducible polynomial by using this primitive irreducible polynomial. So this basic irreducible polynomial will be equal to same like this same degree polynomial, but the coefficient of all of these will be the element of this local Eisenstein ring. So this is a generalized form of the local Eisenstein ring. If alpha is the root of this polynomial, so this is known as the set of all polynomials of degree less than s minus 1. So if we take this s equal to 1, this is known as the integer modulo p power 2s. But if we take n equal to 1, then then the order will be equal to p power 2s. So this becomes Eisenstein field. But if we take p power 2 and s instead of these conditions, so this becomes a local Eisenstein rings of order p power 2 and s. So this local Eisenstein ring consists on the two classes. First class is the unit element, and second class is the non-unit element. I mean zero divisor. So the unit element in the Eisenstein rings, all of these elements of the local Eisenstein rings are given in this PDF. First of all, I am explaining generalized form. Unit element in the local ring consists on the maximal cyclic subgroup and silo p subgroup and the direct product of all of these. So these unit element in the local Eisenstein rings consist on the three classes. First is maximal cyclic subgroup of the group of the unit element GS, whose order is p power 2s minus 1. And second is the silo p subgroup SP, whose order is p power 2s. This will be equal to identity plus multiplicative identity plus maximal ideal. And this indicates the direct product of these two. So the order of the unit element will be equal to this. Ideal structure of the local Eisenstein ring p power 2 and s. So it depends on the value of the p. So if we will multiply this p by the element of the local Eisenstein rings, so it gives us all element of the ideals of the local Eisenstein rings. So this is a generalized form. And also if we multiply this p by this set of all polynomials of degree less than s, and all element will be the local element, local Eisenstein rings. So this becomes also a polynomial of set of all polynomials of degree less than s. So this is a general form of the ideal structure of the local Eisenstein rings. Now, what is the nilpotent element in the local Eisenstein ring? All elements in the local Eisenstein rings are the nilpotent if the coefficient are nilpotent in Zp and omega. It means that all polynomials from the local Eisenstein rings are nilpotent if the coefficients are nilpotent in this local ring. So the order of the nilpotent is also p power 2s. This is the example. Discuss the structure of the local Eisenstein ring 16.2. This is the smallest local Eisenstein rings. Its order will be equal to 16 square. It means that it consists on the 16 power 256 element. So here p is 2 because we can write this 2 power 2 into 2. Z2 power 2 indicates Z2 omega. And the degree of polynomial is 2, this 2, and also value of n is 2. So local Eisenstein ring consists in this local rings, quotient rings. So we need to find a maximal ideal. We need this basic irreducible polynomial by using Hens's lemma. So we can get a maximal ideal fx. Now, the element of the Galois ring 16, 2 are given in this table. These are order of this is 256. All of these are the element of the local Argentine ring 16, 2. Now we want to find the nilpotent element in the local Argentine ring. So the nilpotent element in the local Argentine rings will be p power 2s. So here p is 2 and s is 2. Also this becomes 2 power 4. So these will be 16 elements, and all of those elements which are the nilpotent in local ring. So here is 2 is nilpotent with 16. Similarly, 0 and also 4, all of these linear combinations which are given in the table. All shaded element in this table are the nilpotent element. This is also nilpotent. Similarly, all others shaded element in the table are the nilpotent. But remaining element are the unit element. All other remaining element, because the cardinality of the local Argentine rings is 256 and 16 are the nilpotent element. All others are the unit elements, 240. So these units element consist on the two classes. One is the maximal cyclic subgroup and other is the silo p subgroup. Order of the maximal cyclic subgroup is p power 2s minus 1. So it means that it consists on the 15 element. And the order of the SP is p power 2s. It consists on the 16 element. These are also given in the table. These are the element of the GS maximal cyclic subgroup and the element of the silo P subgroup. We need to find a BCH code by using these maximal cyclic subgroup of the group of the unit element in the local Argentine rings. It means that we need to find the BCH code by using the element of the GS. So these elements of the GS are 16. So we will apply a same procedure like as a BCH code over the Eisenstein field. But we will use the element of the GS, maximal cyclic subgroup. So we need to find the generator polynomial. It will be also same as like as a minimal polynomial. But in this, for finding this polynomial, we will use all element of the maximal cyclic subgroup, GS. And also apply a same procedure. So construct a BCH code over the maximal cyclic subgroup of the group of the local Argentine rings 16 to with design distance 3. So this is given in the PDF. This is a basic irreducible polynomial by using Hens's lemma. So we will use this polynomial under modulo 4 and we get all element for the construction of the maximal cyclic subgroup. So these elements are 30, but length of code is 15. So it means that alpha square is the generator of this maximal cyclic subgroup. So GS will be equal to beta square, beta 15. After that, we will apply the procedure beta 15th root of unity and we use the variation of j equal to 1, 2 because the design distance is 3. So variation will be 2. So it means that we will find if beta is the element of extension field, we will find a first minimal polynomial by using this beta 4 like as a Eisenstein field. Similarly, another polynomial M2 will be found by using the beta scale, and Gx will be the LCM of all these minimal polynomials. So here the degree of the polynomial will be same. So we get a BCH code of 15, 11, 3 with design distance 3 and dimension of code is 11. So I am comparing this work with the existing work. These are the result of the design distance versus dimension of the BCH code over the finite field and Eisenstein field. These are the upper line indicate the results of the BCH code over the Eisenstein field, and the second line indicate the results of the BCH code over the finite field. Similarly, the comparisons of the design of the BCH code over the finite field, and upper is the Eisenstein field results. This is the code rate of the BCH code. This code rate consists on the dimension, depends on the dimension and the length of code. This code R equal to K by N. We conclude that if we use Eisenstein field or local Eisenstein rings, the maximal cyclic subgroup of the local maximal cyclic subgroup of the group of the unit element in the local Eisenstein ring, so we will get a huge number of code words. It means that if we get a more number of code words, then the error correction capability transmission will be slow and the error correction capability will be increased. Similarly, we can expand this work over the quaternion field, 4-dimensional field, and also local quaternion field. These are the references. Thank you. Do you have any question?
Dr. Muhammad, we have 1 minute for question or comments. I don't know.
Yes.
Excuse me. ¿Preguntas? Okay. Everything was clear.
Okay, thank you.
Okay. One question. You have a software code of your algorithms in something like Python or MATLAB, something like that?
Yes. These calculations are very huge. We cannot find these results by using hand. We cannot find. So I am using a Python program. I am using this Python. I am opening this. You can see. And also I am using a MATLAB. I am using this Python program Spider version 5. I get all of these results by using this Python, and also I am using a MATLAB.
Okay, perfect.
I am using this language.
Okay. Okay.
For the construction of the quaternion field, for the construction of the separation of the Eisenstein field, Gaussian field. This is the Eisenstein field program.
¿Otra pregunta? Sí, a veces, pero hay uno más especializado. Okay, thank you so much. This was a real pleasure for I to hear your talk. Very nice talk. Congratulations for your recent degree.
Thank you.
And see you in the next opportunity.
Inshallah.
Thank you.
Bye. Allah.
Bueno, agradecemos a todas las personas que se vincularon a esta transmisión a través del canal de YouTube. Asimismo, agradecemos al doctorado en Ciencias de la Educación de la UPTC, quien nos brindó los apoyos logísticos para que esta transmisión se pudiese hacer en vivo y para que la pudiesen observar en directo nuestros compañeros de la licenciatura en Matemáticas de la UPTC Sede de Duitama. Profesor Muhammad, thank you very much.
Thank you very much. Thank you.
See you very soon. Muchas gracias a todos.
Okay.
Hasta luego.
Okay,
Invitados a nuestra próxima charla dentro de 8 días. Gracias.
Okay, bye. Okay.
Thank you. Bye bye.
Thank you.